Post-transition metals are a set of metallic elements in the periodic table located between the transition metals to their left, and the metalloids to their right. Depending on where these adjacent groups are judged to begin and end, there are at least 5 competing proposals for which elements to include. The 3 most common contain 6, 10 and 13 elements, respectively. See image. All proposals include gallium, indium, tin, thallium, lead, and bismuth. Physically, post-transition metals are soft or brittle, have poor mechanical strength, and have melting points lower than those of the transition metals. Being close to the metal-nonmetal border, their crystalline structures tend to show covalent or directional bonding effects, having generally greater complexity or fewer nearest neighbors than other metallic elements. Chemically, they are characterized to varying degrees by covalent bonding tendencies, acid-base amphoterism and the formation of anionic species such as aluminates, stannates, and bismuthates in the case of aluminium, tin, and bismuth, respectively. They can also form Zintal phases, half-metallic compounds formed between highly electropositive metals and moderately electronegative metals or metalloids. The name is universally used, but not officially sanctioned by any organization such as the IUPAC. The origin of the term is unclear. One early use was in 1940 in a chemistry text. Alternate names for this group are B subgroup metals, other metals, and P block metals, and at least 11 other labels. Applicable elements. Usually included in this category are the group 13 to 15 metals in periods 4 to 6, gallium, indium and thallium, tin and lead, and bismuth. Other elements sometimes included are the group 11 metals copper, silver and gold, which are usually considered to be transition metals, the group 12 metals zinc, cadmium and mercury, which are otherwise considered to be transition metals, and aluminium, germanium, arsenic, selenium, antimony, tellurium, and polonium, of which germanium, arsenic, antimony, and tellurium are usually considered to be metalloids. Astatine, which is usually classified as a nonmetal or a metalloid, has been predicted to have a metallic crystalline structure. If so, it would be a post-transition metal. Elements 112 to 118, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and oganesson, may be post-transition metals. Insufficient quantities of them have been synthesized to allow sufficient investigation of their actual physical and chemical properties. Which elements start to be counted as post-transition metals depends, in periodic table terms, on where the transition metals are taken to end. In the 1950s, most inorganic chemistry textbooks defined transition elements as finishing at group 10 nickel, palladium and platinum, therefore excluding group 11 copper, silver and gold, and group 12 zinc, cadmium and mercury. A survey of chemistry books in 2003 showed that the transition metals ended at either group 11 or group 12 with roughly equal frequency. Where the post-transition metals end depends on where the metalloids or nonmetals start. Boron, silicon, germanium, arsenic, antimony and tellurium are commonly recognized as metalloids. Other authors treat some or all of these elements as nonmetals. Rationale. The diminished metallic nature of the post-transition metals is largely attributable to the increase in nuclear charge going across the periodic table, from left to right. The increase in nuclear charge is partially offset by an increasing number of electrons, but as these are spatially distributed, each extra electron does not fully screen each successive increase in nuclear charge, and the latter therefore dominates. With some irregularities, atomic radii contract, ionization energies increase, fewer electrons become available for metallic bonding, and ions become smaller and more polarizing and more prone to covalency. This phenomenon is more evident in period 4 to 6 post-transition metals, due to inefficient screening of their nuclear charges by their d10 and in the case of the period 6 metals F14 electron configurations, the screening power of electrons decreases in the sequence S greater than P greater than D greater than F. The reductions in atomic size due to the interjection of the D and F blocks are referred to as, respectively, the Scandidae or D block contraction and the lanthanide contraction. Relativistic effects also increase the binding energy, and hence ionization energy, of the electrons in The 6s shell in gold and mercury, and the 6p shell in subsequent elements of period 6. Nomenclature. The origin of the term post-transition metal is unclear. An early usage is recorded by Deming, in 1940, in his well-known book Fundamental Chemistry. He treated the transition metals as finishing at group 10 nickel, palladium and platinum. He referred to the ensuing elements in periods 4 to 6 of the periodic table: copper to germanium, silver to antimony, gold to polonium, in view of their underlying D10 electronic configurations, as post-transition metals. Descriptive chemistry. This section outlines relevant physical and chemical properties of the elements typically or sometimes classified as post-transition metals. For complete profiles, including history, production, specific uses, and biological roles and precautions, see the main article for each element. Abbreviations: mH, Moss hardness, BCN, bulk coordination number. Group 11. The group 11 metals are typically categorized as transition metals given they can form ions with incomplete d shells. Physically, they have the relatively low melting points and high electronegativity values associated with post-transition metals. The filled d subshell and free s electron of Cu, Ag, and O contribute to their high electrical and thermal conductivity. Transition metals to the left of group 11 experience interactions between s electrons and the partially filled d subshell that lower electron mobility. Chemically, the group 11 metals in their +1 valence states show similarities to other post-transition metals, they are occasionally classified as such. Copper is a soft metal Mh 2.5 to 3.0 with low mechanical strength. It has a close-packed face-centered cubic structure BCN 12. Copper behaves like a transition metal in its preferred oxidation state of +2. Stable compounds in which copper is in its less preferred oxidation state of +1, copper 1 chloride, copper 1 bromide, Cu and CuCN, for example, have significant covalent character. The oxide CuO is amphoteric, with predominating basic properties. It can be fused with alkali oxides M2O, M. Na, K, to give anionic oxycuprates M2 copper 4 oxide. Copper forms Zintal phases such as Li7 copper 8 silicide and M3 copper 4 antimonide M. Y, La, Ce, Pr, Nd, Sm, Gd, Tb, Di, Ho, or Silver is a soft metal Mh 2.5 to 3 with low mechanical strength. It has a close-packed face-centered cubic structure BCN 12. The chemistry of silver is dominated by its +1 valence state in which it shows generally similar physical and chemical properties to compounds of thallium, a main group metal, in the same oxidation state. It tends to bond covalently in most of its compounds. The oxide is amphoteric, with basic properties predominating. Silver forms a series of oxorgantates M3 silver 4 oxide, M. Na, K, Rb. It is a constituent of Zintal phases such as Li2AgM M. Al, Ga, In, Tl, C, J, Sn or Pb and Yb3 Ag2. Gold is a soft metal Mh 2.5 to 3 that is easily deformed. It has a close-packed face-centered cubic structure BCN 12. The chemistry of gold is dominated by its +3 valence state. All such compounds of gold feature covalent bonding, as do its stable +1 compounds. Gold oxide, gold 3 oxide is amphoteric, with acidic properties predominating. It forms anionic hydroxoaurates M, gold 4 hydroxide, where M Na, K, 1/2 Ba, Tl, and aurates such as NaO2. Gold is a constituent of Zintal phases such as M2-Aba M. Li or Na, Li2AuM M equals In, Tl, J, Pb, Sn and Ca5O4. Roentgenium is expected to be similar to its lighter homologue gold in many ways. It is expected to have a close-packed body-centered cubic structure. It should be a very dense metal, with its density of 28.7 grams per cc surpassing all known stable elements. Roentgenium chemistry is expected to be dominated by the +3 valence state, similarly to gold, in which it should similarly behave as a transition metal. Roentgenium oxide Rg2O3 should be amphoteric. Stable compounds in the -1, +1, and +5 valence states should also exist, exactly analogous to gold. Roentgenium is similarly expected to be a very noble metal. The standard reduction potential for the Rg3+, Rg couple is expected to be +1.9 volts, more than the +1.52 volts for the O3+, O couple that is the highest among the stable metals. This is exceeded only by darmstadtium, roentgenium, and copernicium among the superheavy metals. The Rg(H2O) cation is expected to be the softest among the metal cations. Due to relativistic stabilization of the 7th subshell, Roentgenium is expected to have a full s subshell and a partially filled d subshell, instead of the free s electron and full d subshell of copper, silver, and gold. Group 12. On the Group 12 transition metals zinc, cadmium and mercury, Smith observed that, "Textbook writers have always found difficulty in dealing with these elements. There is an abrupt and significant reduction in physical metallic character from Group 11 to Group 12. Their chemistry is that of main group elements. A 2003 survey of chemistry books showed that they were treated as either transition metals or main group elements on about a 50-50 basis. The IUPAC Red Book notes that although the Group 3-12 elements are commonly referred to as the transition elements, the Group 12 elements are not always included. The Group 12 elements do not satisfy the IUPAC Gold Book definition of a transition metal. Zinc is a soft metal Mh2.5 with poor mechanical properties. It has a crystalline structure BCN6+6 that is slightly distorted from the ideal. Many zinc compounds are markedly covalent in character. The oxide and hydroxide of zinc in its preferred oxidation state of +2, namely ZnO and zinc hydroxide, are amphoteric. It forms anionic zincates in strongly basic solutions. Zinc forms zintal phases such as LiZn, NaZn13 and Bazn13. Highly purified zinc, at room temperature, is ductile. It reacts with moist air to form a thin layer of carbonate that prevents further corrosion. Cadmium is a soft, ductile metal Mh2.0 that undergoes substantial deformation, under load, at room temperature. Like zinc, it has a crystalline structure BCN6+6 that is slightly distorted from the ideal. The halides of cadmium, with the exception of the fluoride, exhibit a substantially covalent nature. The oxides of cadmium in its preferred oxidation state of +2, namely CdO and cadmium hydroxide, are weakly amphoteric. It forms cadmates in strongly basic solutions. Cadmium forms zintal phases such as LiCd, RbCd13 and CsCd13. When heated in air to a few hundred degrees, cadmium represents a toxicity hazard due to the release of cadmium vapor. When heated to its boiling point in air just above 1000 K, 725 C, 1340 F, cf steel approximately 2700 K, 2425 C, 4400 F, the cadmium vapor oxidizes with a reddish-yellow flame, dispersing as an aerosol of potentially lethal CdO particles. Cadmium is otherwise stable in air and in water, at ambient conditions, protected by a layer of cadmium oxide. Mercury is a liquid at room temperature. It has the weakest metallic bonding of all, as indicated by its bonding energy 61 kJ per mole and melting point -39 degrees Celsius, which, together, are the lowest of all the metallic elements. Solid mercury Mh1.5 has a distorted crystalline structure, with mixed metallic covalent bonding, and a BCN of 6. All of the group 12 metals, but especially mercury, tend to form covalent rather than ionic compounds. The oxide of mercury in its preferred oxidation state HgO +2, is weakly amphoteric, as is the congener sulfide HgS. It forms anionic thiomercurates such as Na2-mercury-4 sulfide and Bogs-3, in strongly basic solutions. It forms or is a part of zintal phases such as NaHg and K8 in 10Hg.
Mercury is a relatively inert metal, showing little oxide formation at room temperature. Copernicium is expected to be a gas at room temperature, although experiments have so far not succeeded in determining its boiling point with sufficient precision to prove this. Like its lighter congener Mercury, many of its singular properties stem from its closed-shell D10s2 electron configuration as well as strong relativistic effects. Its cohesive energy is even less than that of Mercury and is likely only higher than that of flerovium. Solid copernicium is expected to crystallize in a close-packed body-centered cubic structure and have a very high density of 23.7 grams per cc, surpassing all stable elements. Copernicium chemistry is expected to be dominated by the +2 oxidation state, in which it would behave like a post-transition metal similar to Mercury, although the relativistic stabilization of the 7s orbitals means that this oxidation state involves giving up 6d rather than 7s electrons. A concurrent relativistic destabilization of the 6d orbitals should allow higher oxidation states such as +3 and +4 with electronegative ligands, such as the halogens. Copernicium should be the most noble metal in the periodic system, with a very high standard reduction potential of +2.1 volts expected for the Cn2+, Cn couple. Copernicium oxide (CnO) is expected to be predominantly basic.
Group 13.
Aluminium sometimes is or is not counted as a post-transition metal. It has a well-shielded noble gas core rather than the less well-shielded R3D10, Kr 4D10 or Z4F145D10 core of the post-transition metals. The small radius of the aluminium ion combined with its high charge make it a strongly polarizing species, prone to covalency. Aluminium in pure form is a soft metal Mh3.0 with low mechanical strength. It has a close-packed structure, BCN12, showing some evidence of partially directional bonding. It has a low melting point and a high thermal conductivity. Its strength is halved at 200 degrees Celsius, and for many of its alloys is minimal at 300 degrees Celsius. The latter three properties of aluminium limit its use to situations where fire protection is not required, or necessitate the provision of increased fire protection. It bonds covalently in most of its compounds, has an amphoteric oxide, and can form anionic aluminates. Aluminium forms zintal phases such as Lyell, Ca3 aluminium antimonide, and SrAl2. A thin protective layer of oxide confers a reasonable degree of corrosion resistance.
It is susceptible to attack in low pH 8.5 pH conditions, a phenomenon that is generally more pronounced in the case of commercial purity aluminium and aluminium alloys. Given many of these properties and its proximity to the dividing line between metals and nonmetals, aluminium is occasionally classified as a metalloid. Despite its shortcomings, it has a good strength-to-weight ratio and excellent ductility. Its mechanical strength can be improved considerably with the use of alloying additives. Its very high thermal conductivity can be put to good use in heat sinks and heat exchangers, and it has a high electrical conductivity. At lower temperatures, aluminium increases its deformation strength as do most materials whilst maintaining ductility as do face-centered cubic metals generally. Chemically, bulk aluminium is a strongly electropositive metal, with a high negative electrode potential. Gallium is a soft, brittle metal Mh1.5 that melts at only a few degrees above room temperature. It has an unusual crystalline structure featuring mixed metallic covalent bonding and low symmetry BCN7IE1+2+2+2. It bonds covalently in most of its compounds, has an amphoteric oxide, and can form anionic gallets. Gallium forms zintal phases such as Li2Ga7, K3Ga13 and YBGA2. It is slowly oxidized in moist air at ambient conditions. A protective film of oxide prevents further corrosion. Indium is a soft, highly ductile metal Mh1.0 with a low tensile strength. It has a partially distorted crystalline structure BCN4+8 associated with incompletely ionized atoms. The tendency of indium to form covalent compounds is one of the more important properties influencing its electrochemical behavior. The oxides of indium in its preferred oxidation state of +3, namely in 2O3 and in O3 are weakly amphoteric. It forms anionic indates in strongly basic solutions. Indium forms zintal phases such as LIIN, Na2In and Rb2In3. Indium does not oxidize in air at ambient conditions. Thallium is a soft, reactive metal Mh1.0, so much so that it has no structural uses. It has a close-packed crystalline structure BCN 6+6, but an abnormally large interatomic distance that has been attributed to partial ionization of the thallium atoms. Although compounds in the +1 mostly ionic oxidation state are the more numerous, thallium has an appreciable chemistry in the +3 largely covalent oxidation state, as seen in its chalcogenides and trihalides. It is the only one of the group 13 elements to react with air at room temperature, slowly forming the amphoteric oxide Tl2O3. It forms anionic phthalates such as Tl3TlO3, Na3 teraliters O6, NaTlO2, and KTlO2, and is present as the Tl- phthalide anion in the compound CSTl. Thallium forms Zintal phases, such as Na2 teraliters, Na2K21 teraliters 19, CSTl and senior 5 teraliters 3H. Nihonium is expected to have a hexagonal close-packed crystalline structure, albeit based on extrapolation from those of the lighter group 13 elements. Its density is expected to be around 16 grams per cc. With a standard electrode potential of +0.6 volts for the NH+, couple, it should be between copper and silver in inertness. The relativistic stabilization of the 7's electrons has reached the point where the +3 oxidation state should not exist, and hence nihonium should predominantly form the +1 oxidation state. Because of the shell closure at fluorovium caused by spin-orbit coupling, nihonium is also 1/7p electron short of a closed shell and would hence form a -1 oxidation state. In both the +1 and -1 oxidation states, nihonium should show more similarities to astatine than thallium. The NH+ ion is expected to also have some similarities to the Ag+ ion, particularly in its propensity for complexation. Nihonium oxide NH2O is expected to be amphoteric. Group 14. Germanium is a hard MH6, very brittle semi-metallic element. It was originally thought to be a poorly conducting metal but has the electronic band structure of a semiconductor. Germanium is usually considered to be a metalloid rather than a metal. Like carbon as diamond and silicon, it has a covalent tetrahedral crystalline structure BCN4. Compounds in its preferred oxidation state of +4 are covalent. Germanium forms an amphoteric oxide, germanium oxide and anionic germanates, such as Mg2 germanium oxide. It forms Zintal phases such as Lea, K8J44 and La4J3. Tin is a soft, exceptionally weak metal Mh1.5. A 1 cm thick rod will bend easily under mild finger pressure. It has an irregularly coordinated crystalline structure BCN4+2 associated with incompletely ionized atoms. All of the group 14 elements form compounds in which they are in the +4, predominantly covalent, oxidation state. Even in the +2 oxidation state, tin generally forms covalent bonds. The oxides of tin in its preferred oxidation state of +2, namely SNO and tin 2 hydroxide, are amphoteric. It forms stanites in strongly basic solutions. Below 13 degrees Celsius (55.4 degrees Fahrenheit), tin changes its structure and becomes gray tin, which has the same structure as diamond, silicon and germanium BCN4. This transformation causes ordinary tin to crumble and disintegrate since, as well as being brittle, gray tin occupies more volume due to having a less efficient crystalline packing structure. Tin forms Zintal phases such as Na4SN, BASN, K8SN25 and Ca31SN20. It has good corrosion resistance in air on account of forming a thin protective oxide layer. Pure tin has no structural uses. It is used in lead-free solders, and as a hardening agent in alloys of other metals, such as copper, lead, titanium and zinc. Lead is a soft metal Mh1.5, but hardens close to melting, which, in many cases, is unable to support its own weight. It has a close-packed structure BCN12 but an abnormally large interatomic distance that has been attributed to partial ionization of the lead atoms. It forms a semi-covalent dioxide lead-4 oxide, a covalently bonded sulfide PbS, covalently bonded halides, and a range of covalently bonded organolead compounds such as the lead mercaptan Pb Sc2H5 lead tetraacetate Pb CH3CO2 and the once common, anti-knock additive, tetraethyl lead CH3CH2 petabits. The oxide of lead in its preferred oxidation state PbO, +2 is amphoteric, it forms anionic plumbates in strongly basic solutions. Lead forms Zintal phases such as CsPb, senior 31 petabits 20, La5 petabits 3N and Yb3 petabits 20. It has reasonable to good corrosion resistance. In moist air it forms a mixed gray coating of oxide, carbonate and sulfate that hinders further oxidation. Flerovium is expected to be a gaseous metal due to spin-orbit coupling, tearing apart the 7p subshell, so that its 7s 27p1 22nd valence configuration forms a quasi-closed shell similar to those of mercury and copernicium. Indeed, experimental evidence suggests that it has a boiling point of around -60 degrees Celsius, which is by far the lowest of all the metals. Solid flerovium should have a hexagonal close-packed structure and be a rather dense metal, with a density of around 14 grams per cc. Flerovium is expected from its standard electrode potential of +0.9 volts for the Florida 2+, Florida couple to have similar nobility to palladium. Flerovium oxide is expected to be amphoteric, forming anionic flerovates in basic solutions. Group 15. Arsenic is a moderately hard Mh3.5 and brittle semi-metallic element. It is commonly regarded as a metalloid, or by some other authors as either a metal or a non-metal. It exhibits poor electrical conductivity which, like a metal, decreases with temperature. It has a relatively open and partially covalent crystalline structure BCN3+3. Arsenic forms covalent bonds with most other elements. The oxide in its preferred oxidation state as 2O3+3 is amphoteric, as is the corresponding oxoacid in aqueous solution hydrogen arsenite and congener sulfide as 2S3. Arsenic forms a series of anionic arsenates such as sodium arsenite and Pb-HaSO4, and Zintal phases such as sodium arsenide, calcium arsenide and SrAs3. Antimony is a soft Mh3.0 and brittle semi-metallic element. It is commonly regarded as a metalloid, or by some other authors as either a metal or a non-metal. It exhibits poor electrical conductivity which, like a metal, decreases with temperature. It has a relatively open and partially covalent crystalline structure BCN3+3. Antimony forms covalent bonds with most other elements. The oxide in its preferred oxidation state antimony 3 oxide, +3 is amphoteric. Antimony forms a series of anionic antimonites and antimonates such as NaSbO2 and AlSbO4, and Zintal phases such as potassium antimonide, senior 2Sb3 and barium antimonide. Bismuth is a soft metal Mh2.5 that is too brittle for any structural use. It has an open packed crystalline structure BCN3+3 with bonding that is intermediate between metallic and covalent. For a metal, it has exceptionally low electrical and thermal conductivity. Most of the ordinary compounds of bismuth are covalent in nature. The oxide, bismuth 3 oxide is predominantly basic but will act as a weak acid in warm, very concentrated Co. It can also be fused with potassium hydroxide in air, resulting in a brown mass of potassium bismuthate. The solution chemistry of bismuth is characterized by the formation of oxyanions. It forms anionic bismuthates in strongly basic solutions. Bismuth forms Zintal phases such as Nabi, Rb7 in 4x6 and Ba11 Cd8x14. Baylor et al. Refer to bismuth as being the least metallic metal in its physical properties, given its brittle nature and possibly the lowest electrical conductivity of all metals.
Moscovium is expected to be a quite reactive metal, with a similar standard reduction potential to that of aluminium -1.5 volts for the Mc+Mc couple. This increased reactivity is consistent with the quasi-closed shell of flerovium and the beginning of a new series of elements with the filling of the loosely bound 7p3/2 subshell, and is rather different from the relative nobility of bismuth. Like thallium, moscovium should have a common +1 oxidation state and a less common +3 oxidation state, although their relative stabilities may change depending on the complexing ligands or the degree of hydrolysis. Moscovium I oxide Mc2O should be quite basic, like that of thallium, while moscovium oxide Mc2O3 should be amphoteric, like that of bismuth.
Group 16.
Selenium is a soft Mh2.0 and brittle semi-metallic element. It is commonly regarded as a nonmetal, but is sometimes considered a metalloid or even a heavy metal. Selenium has a hexagonal polyatomic CN2 crystalline structure. It is a semiconductor with a band gap of 1.7 electron volts, and a photoconductor, meaning its electrical conductivity increases a millionfold when illuminated. Selenium forms covalent bonds with most other elements, noting it can form ionic selenides with highly electropositive metals. The common oxide of selenium, selenium trioxide, is strongly acidic. Selenium forms a series of anionic selenites and selenates such as sodium selenite, sodium selenide O5, and sodium selenate, as well as zintal phases such as cesium selenide. Tellurium is a soft Mh2.25 and brittle semi-metallic element. It is commonly regarded as a metalloid, or by some authors either as a metal or a nonmetal. Tellurium has a polyatomic CN2 hexagonal crystalline structure. It is a semiconductor with a band gap of 0.32 to 0.38 electron volts. Tellurium forms covalent bonds with most other elements, noting it has an extensive organometallic chemistry and that many tellurides can be regarded as metallic alloys. The common oxide of tellurium TeO2 is amphoteric. Tellurium forms a series of anionic tellurites and tellurates such as sodium tellurite, Na6-TeO6, and rubidium tellurite O9, the last containing tetrahedral TeO2-4 and trigonal bipyramidal TeO4-5 anions, as well as zintal phases such as sodium telluride. Polonium is a radioactive, soft metal with a hardness similar to lead. It has a simple cubic crystalline structure characterized, as determined by electron density calculations, by partially directional bonding, and a BCN of 6. Such a structure ordinarily results in very low ductility and fracture resistance. However, polonium has been predicted to be a ductile metal. It forms a covalent hydride. Its halides are covalent, volatile compounds, resembling those of tellurium. The oxide of polonium in its preferred oxidation state, polonium-4 oxide, +4, is predominantly basic, but amphoteric if dissolved in concentrated aqueous alkali, or fused with potassium hydroxide in air. The yellow polonate IV ion polonium-4 oxide -3 is known in aqueous solutions of low Cl concentration and high pH. Polonides such as Na2PO, BePO, ZnPO, CdPO and HgPO feature Po2- anions. Except for HgPO, these are some of the more stable of the polonium compounds. Livermorium is expected to be less reactive than moscovium. The standard reduction potential of the Lv2+, Lv couple is expected to be around +0.1 V. It should be most stable in the +2 oxidation state. The 7p3 electrons are expected to be so weakly bound that the first two ionization potentials of livermorium should lie between those of the reactive alkaline earth metals magnesium and calcium. The +4 oxidation state should only be reachable with the most electronegative ligands. Livermorium oxide LVO should be basic and livermorium IV oxide LVO2 should be amphoteric, analogous to polonium.
Group 17.
Astatine is a radioactive element that has never been seen. A visible quantity would immediately be vaporized due to its intense radioactivity. It may be possible to prevent this with sufficient cooling. Astatine is commonly regarded as a nonmetal, less commonly as a metalloid and occasionally as a metal. Unlike its lighter congener iodine, evidence for diatomic astatine is sparse and inconclusive. In 2013, on the basis of relativistic modeling, astatine was predicted to be a monatomic metal, with a face-centered cubic crystalline structure. As such, astatine could be expected to have a metallic appearance, show metallic conductivity, and have excellent ductility, even at cryogenic temperatures. It could also be expected to show significant nonmetallic character, as is normally the case for metals in, or in the vicinity of, the p block. Astatine oxyanions Auto-3 and Auto-4 are known, oxyanion formation being a tendency of nonmetals. The hydroxide of astatine monohydroxide is presumed to be amphoteric. Astatine forms covalent compounds with nonmetals, including hydrogen astatide HAT and carbon tetraastatide CAT4. At-N ions have been reported to form astatides with silver, thallium, palladium and lead. Przezinski et al. Note that astatide ions should form strong complexes with soft metal cations such as Hg2+, Pd2+, Ag+, and Tl3+. They list the astatide formed with mercury as mercury 1-hydroxide at tennessine, despite being in the halogen column of the periodic table, is expected to go even further towards metallicity than astatine due to its small electron affinity. The -1 state should not be important for tennessine and its major oxidation states should be +1 and +3, with +3 more stable. Ts3+ is expected to behave similarly to O3+ in halide media.
As such, tennessine oxide Ts2O3 is expected to be amphoteric, similar to gold oxide and astatine oxide. Group 18. Oganesson is expected to be a very poor noble gas, and may even be metallized by its large atomic radius and the weak binding of the easily removed 7p3 electrons. Certainly it is expected to be a quite reactive element that is solid at room temperature and has some similarities to tin, as one effect of the spin-orbit splitting of the 7p subshell is a partial role reversal of groups 14 and 18. Due to the immense polarizability of oganesson, it is expected that not only oganesson fluoride but also oganesson fluoride should be predominantly ionic, involving the formation of Og2+ and Og4+ cations. Oganesson oxide and oganesson oxide OGO2 are both expected to be amphoteric, similar to the oxides of tin. Related groupings. B subgroup metals. Superficially, the B subgroup metals are the metals in groups IB to VIB of the periodic table, corresponding to groups 11 to 16 using current IUPAC nomenclature. Practically, the group 11 metals copper, silver and gold are ordinarily regarded as transition metals or sometimes as coinage metals, or noble metals, whereas the group 12 metals zinc, cadmium, and mercury may or may not be treated as B subgroup metals depending on if the transition metals are taken to end at group 11 or group 12. The B nomenclature, as in groups IB, IIB, and so on, was superseded in 1988 but is still occasionally encountered in more recent literature. The B subgroup metals show nonmetallic properties. This is particularly apparent in moving from group 12 to group 16. Although the group 11 metals have normal close-packed metallic structures, they show an overlap in chemical properties. In their +1 compounds, the stable state for silver, less so for copper, they are typical B subgroup metals. In their +2 and +3 states their chemistry is typical of transition metal compounds. Borderline metals. Parrish writes that, "As anticipated, the borderline metals of groups 13 and 14 have non-standard structures. Gallium, indium, thallium, germanium, and tin are specifically mentioned in this context. The group 12 metals are also noted as having slightly distorted structures. This has been interpreted as evidence of weak directional, i.e. covalent bonding." Chemically weak metals. Rayner, Canham and Overton use the term chemically weak metals to refer to the metals close to the metal-nonmetal borderline. These metals behave chemically more like the metalloids, particularly with respect to anionic species formation. The 9 chemically weak metals identified by them are beryllium, magnesium, aluminum, gallium, tin, lead, antimony, bismuth, and polonium. Fusible metals. Cardarelli, writing in 2008, categorizes zinc, cadmium, mercury, gallium, indium, thallium, tin, lead, antimony and bismuth as fusible metals. Nearly 100 years earlier, Lewis 1911 noted that fusible metals were alloys containing tin, cadmium, lead, and bismuth in various proportions. The tin ranging from 10 to 20%. Heavy metals of low melting point. Van Wert grouped the periodic table metals into A, the light metals, B, the heavy brittle metals of high melting point, C, the heavy ductile metals of high melting point, D, the heavy metals of low melting point Zn, Cd, Hg, Ga, In, Tl, J, Sn, As, Sb, Bi, and Po, and E, the strong, electropositive metals. Britton, Abatiello and Robbins speak of the soft, low melting point, heavy metals in columns Lib, Elia, Eva, and Va of the periodic table, namely Zn, Cd, Hg, Al, Ga, In, Tl, C, J, Sn, Pb, and Bi. The Sargent-Welch chart of the elements groups the metals into light metals, the lanthanide series, the actinide series, heavy metals brittle, heavy metals ductile, and heavy metals low melting point, Zn, Cd, Hg, Cn, Al, Ga, In, Tl, J, Sn, Pb, Florida, Sb, Bi, and Po. Less typical metals.
Hibashi groups the elements into 8 major categories: 1 typical metals, alkaline earth metals, and aluminium; 2 lanthanides, Ce Lu; 3 actinides, THLR; 4 transition metals, Sc, Y, Le, Ac, groups 4 to 10; 5 less typical metals, groups 11 to 12, Ga, In, Tl, Sn and Pb; 6 metalloids, B, C, J, As, Se, Sb, Te, Bi and Po; 7 covalent nonmetals, H, C, N, O, P, S and the halogens, and 8 monatomic nonmetals, that is, the noble gases.
Metametals. The metametals are zinc, cadmium, mercury, indium, thallium, tin and lead. They are ductile elements but, compared to their metallic periodic table neighbors to the left, have lower melting points, relatively low electrical and thermal conductivities, and show distortions from close-packed forms. Sometimes beryllium and gallium are included as metametals despite having low ductility. Ordinary metals.
Abrikosov distinguishes between ordinary metals, and transition metals where the inner shells are not filled. The ordinary metals have lower melting points and cohesive energies than those of the transition metals. Gray identifies as ordinary metals, aluminium, gallium, indium, thallium, nihonium, tin, lead, fluorovium, bismuth, moscovium, and livermorium. He adds that, "In reality most of the metals that people think of as ordinary are in fact transition metals."
Other metals. As noted, the metals falling between the transition metals and the metalloids on the periodic table are sometimes called other metals. See also, for example, Taylor et al. Other, in this sense has the related meanings of existing besides, or distinct from, that already mentioned. That is, the alkali and alkaline earth metals, the lanthanides and actinides, and the transition metals. Auxiliary, ancillary, secondary. According to Gray, there should be a better name for these elements than other metals. P-block metals. The P-block metals are the metals in groups 13 to 16 of the periodic table. Usually, this includes aluminium, gallium, indium and thallium, tin and lead, and bismuth. Germanium, antimony and polonium are sometimes also included, although the first two are commonly recognized as metalloids. The p-block metals tend to have structures that display low coordination numbers and directional bonding. Pronounced covalency is found in their compounds, the majority of their oxides are amphoteric. Peculiar metals. Slater divides the metals fairly definitely, though not perfectly sharply, into the ordinary metals and the peculiar metals, the latter of which verge on the nonmetals. The peculiar metals occur towards the ends of the rows of the periodic table and include approximately gallium, indium, and thallium, carbon, silicon, both of which have some metallic properties, though we have previously treated them as nonmetals. Germanium and tin, arsenic, antimony, and bismuth, and selenium, which is partly metallic, and tellurium. The ordinary metals have centrosymmetrical crystalline structures, whereas the peculiar metals have structures involving directional bonding. More recently, Joshua observed that the peculiar metals have mixed metallic covalent bonding. Poor metals. Farrell and Van Sishen use the term poor metal, for simplicity, to denote one with a significant covalent, or directional character. Hill and Hallman observe that, "The term poor metals is not widely used, but it is a useful description for several metals including tin, lead and bismuth. These metals fall in a triangular block of the periodic table to the right of the transition metals. They are usually low in the activity electrochemical series and they have some resemblances to non-metals." Reed et al. Write that, "poor metals" is an older term for metallic elements in groups 13 to 15 of the periodic table that are softer and have lower melting points than the metals traditionally used for tools. Semimetals. In modern use, the term semimetal sometimes refers, loosely or explicitly, to metals with incomplete metallic character in crystalline structure, electrical conductivity or electronic structure. Examples include gallium, ytterbium, bismuth, mercury and neptunium. Metalloids, which are in between elements that are neither metals nor nonmetals, are also sometimes instead called semimetals. The elements commonly recognized as metalloids are boron, silicon, germanium, arsenic, antimony and tellurium. In Old Chemistry, before the publication in 1789 of Lavoisier's revolutionary elementary treatise on chemistry, a semimetal was a metallic element with very imperfect ductility and malleability, such as zinc, mercury or bismuth. Transition metals. Historically, the transition metals series includes those elements of the periodic table which bridge the gap between the very electropositive alkali and alkaline earth metals and the electronegative non-metals of the groups, nitrogen phosphorus, oxygen sulfur, and the halogens. Cherinis, Parsons and Ronberg wrote that, the transition metals of low melting point form a block in the periodic table, those of groups 2b, zinc, cadmium, mercury, 3b, aluminium, gallium, indium, thallium, and germanium, tin and lead in group 4. These metals all have melting points below 425 degrees Celsius. Notes. Sources. Citations. Indexed references.